In this section, I will discuss decision trees on balance scale dataset. So, first of all, drag and drop your repository. Next step, we want to split the data into testing and training datasets. So, we use the cross validation operator. And in the cross validation operator, in the testing section, we want to draw a decision tree. So, you'll go in the modeling. Classification and regression, tree induction, decision tree. In the testing section, we'll apply the model that was generated by this decision tree, and to evaluate it or to measure its performance, we use the performance operator. Connect the ports. That's it. And now in the main process, we have to connect the ports. That's it. Everything is ready now. And let me first discuss the decision tree and its parameters in a little detail now. You can find the help regarding the parameters in the help window as well. Here you see the first one is the criteria. It specifies the use criterion for selecting attributes and numerical splits. It can have values gain ratio, information gain, Gini index, and accuracy, but by default it is gain ratio. Minimal size of split. It explains the minimal size of a node in order to allow a split. So default value is 4. Minimal leaf size. This explains the minimal size of all the leaves. Minimal gain. It explains the minimal gain which must exist if there should be any split. And next we have maximal depth, confidence, number of pre-pruning alternatives, etc. So maximal depth shows the maximum depth of the tree. So because if the depth of the tree is very huge, it becomes very difficult to understand that tree, so we can reduce the maximal depth of the tree. Confidence value suggests the confidence level used for the pessimistic error calculation of pruning. So number of pre-pruning and pre-pruning is basically used to remove those nodes that are placed uselessly to make the tree more understandable and more useful. So by default, pruning and pre-pruning both are used. If you don't want to use them, you can check one of these checkboxes. So let us create the decision tree. Here you go. This is the decision tree. You see these different colors at each node show that there are different type of answers that we have got for this particular classification. So we can modify this by going back and changing this minimum leaf size 1. This will give more accurate answers. Now every node should be of a single color. Here you go. Now all the nodes are of different colors. Each node is of a single color, sorry. Now this tree is a little too big. Let me use a radial view. Here you go. So see, this is a huge tree. I wasn't expecting such a large tree. This tree is so big because it just checks every possible value. You see, it takes the left weight and takes its 5 values and compares it with, say we take the value 1, it compares it with the right weight, and then it takes its 5 values, and for each 5 values it will take left distance, take its all 5 values, then it will take right distance and compare its all 5 values. So this is not a very good way to design a tree, this will give us 625 different nodes. So I wasn't expecting such a huge tree, but there is a good reason why such a huge tree was constructed. Let us first examine the performance, then I'll come back to this discussion. The performance is also not very good, just 49% accurate. But one thing you should note over here is that it still classified some of attributes as balanced. So this was not the case in uh, the previous two KNN and Naïve based algorithms. They failed to classify an attribute with very few instances. So this is one plus point of the decision tree, but the accuracy is miserably bad. It is 50% just. So let me come back to the discussion of why such a huge tree was constructed, and we were actually expecting a better, a shorter, a more concise tree. The reason is that there are 625 different instances, so just to classify them there are 625 different possibilities, and it goes through all those 625 possibilities. But the thing is, we already knew that if a certain formula, we in the introduction of the data we mentioned that if left weight, the product of left weight and left distance is greater than the product of right weight and right distance, so we can use this equation to classify them, and on that basis we could have had a very simple tree. But the thing is, that is a formula, or that is a thing that we know before the use of this algorithm, but the algorithm was not given any such pre-information about the dataset. So if that information is given to the dataset, I think this algorithm can perform much better. So let's try this. We go and try some things to just we generate the tree, this time with a little pre-processing. So let's